Welcome to Suni Science World. In the last video, I had discussed about the relationship between temperature and kinetic energy, and also we discussed the definition and units of specific heat. Now, I am going to discuss about the third part of heat lesson. In this video, we are going to know about specific heat in detail. Before starting the video, please like, share and subscribe to my channel. Now, in this video, we are going to know the answer for the question, why is the specific heat different for different substances? Let us find out the answer. We know that the temperature of a substance is directly proportional to the average kinetic energy of particles of the substance. The molecules of the substance or system have different forms of energies such as linear kinetic energy, rotational kinetic energy, vibrational energy, and potential energy between the molecules. The total energy of the system, that is, the sum of all these energies, that is, linear kinetic energy, rotational kinetic energy, vibrational energy, and potential energy is called internal energy of the system. I will do another video on internal energy of the system, because this video will become lengthy if I include that video. So, let me do that in my next video. So, sum of all these energies of the system is called internal energy of the system. When we supply heat energy to the system, the heat energy given to it will be shared by the molecules among the various forms of energy. This sharing of heat energy will vary from substance to substance. If the share of heat energy is utilized for increasing its linear kinetic energy is maximum, then the rise in temperature is high for a substance. This sharing of heat energy of the system also varies with temperature. That is, if the temperature of a substance is low, then the share of heat energy is utilized for increasing its linear kinetic energy is also low. That is why the specific heat is different for different substances. Now we see what are the values of specific heat for different substances. This table shows the values of specific heat for different substances. The values are given both in CGS and SI units, that is, in calorie per gram degree C and also in joule per kg Kelvin. If you observe the table, water has the highest specific heat among the substances given in the table. That is, the specific heat of water is 1 calorie per gram degree C. And the substance which has lowest specific heat value from the table is lead. That is 0.031 calorie per gram degree C. Now, I am going to discuss about the applications of specific heat capacity. The first application of specific heat capacity is the oceans behave like heat storehouses for the earth. Why the oceans behave like heat storehouses? This is because of the higher specific heat of water. Why this happens and how it is useful for us, let us know. We know that the sun delivers a large amount of energy to the earth daily. The water sources on the earth like oceans absorb this energy and they maintain a constant temperature. Like this, oceans behave like heat storehouses for the earth. We know that the temperature at the equator is high. So, oceans can absorb large amounts of heat at the equator without much rise in temperature. This is because of high specific heat of water. As the heat is absorbed by the oceans, the temperature is cooled down and moderate the surrounding temperature near the equator. Then, the heat absorbed by the water in oceans is transported away from the equator to areas closer to the north and south poles. We know that the climate at north and south poles is very cold. This transported heat helps to moderate the cold climate in parts of the earth that are far from the equator. Now we go for next application. When we keep a watermelon in refrigerator, it retains its coolness for a longer time than any other fruit. Why this particular fruit retains its coolness for a longer time? This is because it contains a large percentage of water and water has a high specific heat. So, watermelon retains its coolness for a longer time than any other fruit. Now we go for next application. When you eat a hot samosa, it appears to be cool outside, but it is hot inside. This is because the curry inside the samosa contains ingredients with higher specific heat. Now we go for another topic, that is method of mixtures. Now we do an activity. In this, first take 2 beakers of same size and pour 200 ml of water in each of them. Now heat the water in both beakers till they attain the same temperature. Let us suppose the temperature should be 60 degrees centigrade. If you pour this water from these 2 beakers into a large beaker and measure the temperature of the mixture, what do you observe? You observe that the temperature of the mixture is also same, that is 60 degrees centigrade. This is because the water in both the beakers is heated to 60 degrees C, and when we mix these two water in beakers, as the temperature is equal, there is no transfer of heat takes place. So the temperature of the mixture is also 60 degrees centigrade. Now take 2 beakers and heat the water in one beaker to 90 degrees centigrade and the water in other beaker to 60 degrees centigrade. Now mix the water from these beakers in a large beaker. What will be the temperature of the mixture? You notice that the temperature of the mixture is 75 degrees Celsius. Because the mass of the water is same, so the temperature of the mixture is the average of the two individual temperatures. So we get the temperature of the mixture is 75 degrees Celsius. Now we go for third situation. Now take 100 ml of water in a beaker and heat it up to 90 degrees Celsius. And take 200 ml of water in another beaker and heat it up to 60 degrees Celsius. And mix the water from these beakers in a larger beaker. What is the temperature of the mixture? And what difference do you notice in the change in temperature? Here, in this case, the mass of the water in two beakers is not same, and also the temperature is different. Then we can't see the value of temperature of mixture by doing average. Then how can we find out the change in temperature for this type of situations? Let us find out. Let the initial temperatures of the water be T1 and T2. The higher of the two temperatures is called T1 and the lower temperature is called T2. Here T1 is 90 degrees Celsius and T2 is 60 degrees Celsius. And let their masses be M1 and M2. Here M1 is equals to 100 ml and M2 is equals to 200 ml. Let T be the final temperature of the mixture. This final temperature is lower than the higher temperature T1, that is less than 90 degrees Celsius, and higher than the lower temperature T2, that is more than 60 degrees Celsius. This means that the hot water has lost heat and the cold water has gained heat. We know that the amount of heat lost or gained by a substance Q is equals to ms delta T, where Q is the amount of heat lost or gained by a substance and m is the mass of the substance. S is the specific heat and delta T is the change in temperature. Now we can write it as the amount of heat lost by the hot water Q1 is equals to M1S into T1 minus T. Because the final temperature is lower than the temperature of hot water, that is T1, and the amount of heat gained by the cold water Q is equals to M2S into T minus T2. Because as the final temperature is more than the temperature of cold water T2, so we can write the change in temperature as T minus T2. If we assume that there is no loss of heat, then heat lost by the hotter substance is equal to the heat gained by the cooler substance. That is, Q1 is equals to Q2, which can be written as M1S into T1 minus T is equals to M2S into T minus T2, which can be simplified to T is equals to M1 T1 plus M2 T2 divided by M1 plus M2. Now, if we substitute the values of M1 M2 and T1 T2 in the above formula, we get the final temperature of the mixture as 70 degrees Celsius. From this, we will notice that the temperatures of mixture in second and third situations are not equal. In second situation, we got 75 degrees Celsius, and in third situation, we got 70 degrees Celsius. Like this, we can find out the final temperature of a mixture even though their masses are not equal. When two or more bodies at different temperatures are brought into thermal contact, then net heat lost by the hot bodies is equal to the net heat gained by the cold bodies until they attain thermal equilibrium. This is known as principle of method of mixtures. So, net heat loss is equals to net heat gain. This is the principle of method of mixtures. Thank you for watching this video. If you like this video, please like, share and subscribe to my channel.